is just a copy of it. So it's big O, another big O. So this is slightly less than big O, but
The second proverb.
on average it's n over 2 because I and j can be from 0 to n. So the middle point is n over 2. So it's n cube complexity algorithm. So I think many number of students say this is a constant, but this is not a constant, right? Because j goes up to n, I can start from 0. So it's from n 0 to n. So on average, you have to consider n over 2 for the average number of iteration for this inside of for loop. So it's n cube because of that. And for this recursive function called, that's the recursive part. And this is n over 2 because left and mid. This is n over 2 left and mid. And this is started about between left and mid and between mid and right at the half point of that. So this is another n over 2 size of the problem. So you have 3 instances of recursive function core here, and then combine is given as n square complexity. So that will be your complexity, the recurrence relation. Tn is 3 times Tn over 2 because 3 instances of recursive function core and n square complexity for other stuff. So if you use Master's theorem, you can easily simplify it. It's n square. So that was the answer I looked for. And if your answer is correct, but your recurrence relation doesn't make sense to me, you didn't get much point. I think I give you only 1 point for such case. And which function grow faster? Log n to the n and log n power of n grow faster because of this analysis. After taking log, we can easily determine this is n times some positive number growing a little bit slower than n, but it can be a very big number if n is big. And this is log n square. So obviously linear complexity grow much faster than log n. So because of that, this equation grow much faster. And for true false, I think this is tedious. So I think if you don't get it, then please come back to my office hour tomorrow. And the only thing worth to discuss is this: if Fn is big O Gn, and Fn is also big O Hn, but Gn, Hn, they don't have any relation. So we cannot say Gn is big O Hn. So it's false. Others are nothing but definition of the asymptotic notation. So I will just skip it. And for this is the variation of the example we had in the class. So the thing we had in the class comparing the ranks of the linked list, here we need to compare the element to 2. This is the simple variation of the example we had in the class. There are many possible solutions, but this is my solution. When we reach the null point at the same time, that means everything up to that point identical, elements are same, and then both of them reach at the null point. That's the only case these two L1 and L2 can be identical. So that case return true. And then the next statement, I check the ranks variation. If L1 reaches null or L2 reaches null, that means only one of them null, right? Because if both of them are null, it should be returned here. So if one of them reaches null point and one of them should be longer, so that I simply return false. And they're not reached the null point yet, then we compare the element. If elements are not equal, then we just return false. if elements are equal, they're still left over, and everything same up to that point, I will just use the recursion. So return recursion L1 next, L2 next. And there are many possible solutions, and I try to understand your answer and try to give you as much as point as possible. So, but I may not understand your algorithm properly. So if you think I did not understand your solution, please come back to me during my office hour or email me. Then I will fix the error. And this problem is, I think, tedious, so I will not go through it. But if you just to follow the line of the code given here, and then see what will be the output from the system out method, and you will find 786. And this one also easy question. This one was not discussed, but it's an easy problem, and previous problem was not discussed, but that was also easy problem. So grocery, almost everyone get the correct answer. I think maybe 100%. In the grocery store, customer service line, obviously, first in, first out. Queue structure should be better. And then this Hansel and Gretel example, the returning path is the reverse of the coming path. So stack will be the better structure to maintain the least path. And this one is very similar to the university registration problem. So multi-list will be the best way to do it. If you just put list or multi-list, you got the full point. And this proof by induction, I will not go through it. You have solution. Your homework assignment is almost identical, except this one was 4. So this one was even easier problem. So I will just move to other part. And this binary search tree insert problem, I don't think we need to talk about it, right? Anybody want me to discuss this solution? Okay, then I will move to the next problem. This one, do anybody have a question for this problem? I think maybe 2/3 of class have answer, but maybe 1/3, maybe 1/2 didn't have the answer. Maybe I quickly discuss this. First order was F, C, I, B, D, H, G, A, E, and in order, I'm writing down the problem to the paper for my document discussion. F, D, C, B, I, E, H, A, G. Okay, let me switch to document. Okay, for this problem, from the first order, we can easily have information the root of the tree is E, because in the first order, left subtree, right subtree, and the parent, so root will be the last element. So we know E should be the root of the tree, and E is here, so they should be in the left subtree, AHG should be in the right subtree. So we ignore everything except FDCPIE, FDCPIE. So that are related to left subtree, right? So here, the information, I don't know the structure of this, but I know FDCPI should be here, and AHG, the right subtree. In terms of FDCPI, if you check the first order, we will ignore everything except those FDCBI. So it clearly says this example first order, D should be the root of the tree. So D should be the root of the subtree. So this one should be D. And D should have F. as rep child, and CBI should be in the right side of D. Okay, so we ignore everything except CBI, CIB, so given here, CIB given here. So B should be the root of the tree because of the last one. So we know D, F, P, and C is the rep subtree. I should be the right child. C, I. Okay, so that is the tree, rep subtree of E. And then we need to figure out AHG. So ignore everything except AHG. So that part is about the character, and this part is it. So the root of the tree is A because A was listed at the last minute. And from this, we know H is the left subtree and G is the right subtree. So if you apply the post order in order traversal at the same time, you will be able to identify the structure of the tree. Okay, so let me go back to the midterm exam solution. Okay, so that's why you have this one as a solution of this tree structure. And printing all number in a descending order. If you understand the property of the binary search tree, for example, we have a binary search tree used in the previous example. If you want to print everything in the reverse order, the right, you have to keep going right here. Print this and the current node and print left child, right? And then 7 is the next largest. So after completion of right subtree, the current node, and left subtree. In terms of 5, in terms of this subtree 5, if you want to print in the reverse order, right subtree, and then current node, and the left subtree, right? If you apply that idea, so if you apply that in the code, if T is not null tree, print T right, and then print T element and print T left. And I think the exam paper include typo. This one should be void, not integer. So I didn't care whatever you return or even you skip the returning value. So anyway, I'm sorry for the typo. It should be void to make it easier, but I put integer by mistake. So because I was changing some of other code and copy and paste it, and I did not change the integer to void. So anyway, if you print the right subtree and current node and the left subtree, everything will be stored in the reverse order. One of common error, I don't know why, but many students check the T left is not null and then print T right. It doesn't make sense to me. Why you check left subtree is not null and then print right subtree? You don't know what is in your right subtree, whether null or not. I don't know where that code come from, but it might be some wrong solution in the web page. I don't know. Anyway, that obviously doesn't make sense to me, so you give only the partial point. So if you check the tree is the null tree or not, then you don't really need to check the right subtree is null or not because it automatically covered by the primitive case. Okay, so that's for the print tree. And I don't think we need to talk about it. So almost to 95% students did very well. There was a few students, maybe 2 to 3 students have a problem here. So I think 90% class did very well for this problem. And this part, question number 5, part B, I found a solution which is directly copy and paste from internet solution. This is the one of the problem coming from the exercise problem of the chapter 7, and I use it, and then I found there are two students copy and paste exactly the same internet solution here. That's a plagiarism. So I just give 0 point for that. But anyway, the idea discussion is distance two sorting is nothing but you make a two subpart with index 0, 2, 4, 6, 8, or even index number one subset, or odd index number one subset. And then you will do insertion sort with a half size item. Have a question? Okay. So for distance two sorting, you will have a two instance of half size problem, and the way you sort it is identical to the insertion sort. Because shell sort will do distance D sort using insertion sort algorithm. So when D is equal to 2, you will have a two instance of half size problem. You will use the insertion sort algorithm for that. The complexity for insertion sort for n over 2 element is n squared, right? More precisely, on average, it's n squared over 4, n squared over 8 more precisely. So anyway, so it's n squared. And after that, merging two sorted one into merged array, insertion sort cannot do merge operation. It requires another n squared complexity step. So big O n squared, big O n squared, it's big O n squared complexity. Okay. And part C was a tedious, so I will not discuss the solution. If there's a minor error like a 12 inversion, 14 inversion, I deduct only 1 point. And totally different answer like a 7 inversion, 4 inversion, then you got 0 point for that. And we went through this problem many times in the quiz and in the assignment. So minimum number of comparisons, you have to use this magic equation, and that's if you use this magic equation when n is equal to 7, you will have 13 as the minimum. So the equation is given here. And is that gonna be applicable to all comparison-based sorting algorithm even not invented? Yes, because every comparison-based sorting algorithm can be represented by a decision tree, and our analysis is based on the theoretical lower bound, the distance from the deepest node from the root of the tree to the farthest leaf in the tree. So there is no way if you can put leaf node any place, but that's the lower bound. So because of that, that lower bound also applicable to any kind of comparison-based sorting algorithm. So answer is yes, and the reason is given in the given here. So if you want, you can copy and paste it. But that was the answer I looked for from your answer sheet. But many students copy and paste the theorem from the textbook, and then because of this theorem, this is true. I cannot say that that's a wrong answer, but for the justification I looked for, you can find the link between decision tree and then lower bound. So the sample answer, reasonably good sample answer is here. So I didn't deduct point for use of the theorem, but that was not the best answer for the problem. And the quicksort, I think quicksort has a problem. Number of students has a problem with the quicksort. So I will discuss this solution during my office hour tomorrow. So if you want to see how quicksort works, please join at 4 o'clock. So I will start from this problem because maybe 1/3 of students, more than half of students did very well. They have a full understanding of quicksort algorithm. Maybe 10%, 15%, they understand the algorithm but made a minor mistake, like forgot swap to the AI at the end of the partitioning or things like that. So some minor error, I deduct only small point for that. So anyway, so I will discuss solution during the office hour because more than half of class know how to do it. And that's the running time for the sorting algorithm with a different input. For insertion sort, best case sorted input n square, worst case reverse order input n square, random input n square. Merge sort complexity doesn't matter with the input, so it's n log n. For the quick sort based on median of 3 selection, median of 3 people selection algorithm, n log n for all cases, but theoretical worst case random input can be n square, but probability of n square complexity is negligible. It will not really happen in real world application. But if you write down n square, that's the only error I did not deduct point because theoretically that's not a wrong answer. And for sorted input n square, and random input n log n on average because it can be the size of S1 can be any value between 0 to n minus 1. So that's an average case. So average case is n log n. So that's why it's n log n. Okay, so that's it for the metamigdam solution. So if you have any question, please join the office hour tomorrow. So I don't want to spend 1 hour of class time for the metamigdam solution. We already spent 30 minutes of class time for that. Okay. Any question or concern for the meeting?
Yeah, I just was wondering, could you go up to part 2A so I could get a screenshot real quick?
Sure, part 2A.
Are all the answers on Canvas?
I will not post the answer on Canvas because I saw my solutions are sold in website or web portal. So if you have a question, I can email you the solution for the given problem, but not for entire solution.
Got it. Yeah. I'll just email you, too. Yeah. It'll make it more easier. Thank you.
Yes, please do. Part B for question number 2. Is that the one?
Yeah, I got it. Thank you.
Okay. So what else? If you want to have a screen capture or... Okay, then if you still don't have a solution for the problem you don't understand, just email me. I can give you a screenshot of my solution. Okay. Stop sharing on this. Then we're gonna return back to the lecture slide. Anyway, my feedback and comparison with in-class version of 3320 versus online version of 3320, the performance is not as good as in-person in class, face-to-face class. So I think because one of my fundamental problem is if you are in front of me and then I can read your face, and so that I can see whether you understand, you're following my discussion or not. But this online format, there is no way I can read from your face. I have no idea whether you fully understand the lecture material, it's boring, or you have no idea what's going on. So that was a real difficulty for me. And some students just to log into the Zoom meeting room and didn't do anything away from the desk. There's no way I can control that. So I think that's probably the main reason. So I ask you to put more effort and be more engaged in during the exercise time instead of doing web surfing or do something else. That's the way you can improve your performance. Okay. So we will discuss splay tree today, and splay tree address similar problem as Abel tree. Splay tree is a binary search tree. So if we try to address problem in a binary search tree, but splay tree does not including any overhead like maintain the height information and checking balance information. Splay tree idea is after bad operation, it rotates the tree blindly. So it doesn't know whether rotation will improve the tree structure or not, but it will likely improve for really after really bad operation. If you do splaying operation, it will likely improve the structure of the tree. So that's the splay tree. So this is one of the bad binary search tree here. The complexity of this binary search tree find operation like 97, it's about big O n over 2. So there are maybe 12, 13 elements there, and you need to going down 1, 2, 3, 4, 5, 6, 7, 8. After A comparison, you'll be able to find 97. So this is obviously a bad binary search tree, and we want to make the tree height better, smaller tree height. So the basic idea in the splay tree algorithm, single operation may take big O n time. However, the sequence of find operation to the deepest node in the tree will not be that bad. So sequence of bad operation will be the problem. It just try to handle the sequence of bad operation. So the discussion in the textbook, we will restructure the tree after every operation because the textbook try to provide more information for the splaying operation. So it splaying after every operation, even insert operation, delete operation, find operation. After every operation, splay tree, given in the textbook, do the splaying and do the rotation. However, in real-world implementation of splay tree, it may not splaying after every operation. It's just to wait some specific threshold value, like a threshold value may be n over 2 or n over k. K can be any positive integer. And if complexity of the code is more than complexity of operation is given over the threshold, and then the tree will restructure. Tree will be restructured by splaying. So how to restructure tree? How to self-adjust? So we will introduce a number of rotation algorithms. So anyway, another important things for splay tree is after accessing node, after inserting 32, for example, we have to splay 32. So after splaying, the node will become the root of the tree. And this approach somewhat makes sense because in programming, there is something called data locality. The data locality means if you access X, and you will likely access X again in near future. So freeing the most recent access node at the top of the tree can be beneficial. Like if you have a 3 variable X, Y, and Z, most of the time you will use only those 3 elements for some operation, then splaying tree might be the perfect way to minimize the complexity of your algorithm. So anyway, note that the splaying tree, when you access node X, we will do some kind of rotation and make x as the root of the tree. Then now we are ready to discuss the rotation. In splaying tree rotation, there are 4 more rotations. Actually, altogether there are 6 rotations. However, many rotations are overlapped with A-wheel tree rotation. So what you need to memorize is this jig-jig rotation. So splay tree make node push up only 2 level up for seeing 1 rotation. So we have to repeatedly splay until you reach the top of the tree. So the jig-jig rotation, when you are now you have to move in a single direction. In that case, left up, right, right. You have to go push up the left child and push up left child in a root of the tree. And then this is the jig-jig rotation. For jig-jig rotation, if you have an original sequence CBA, and then after rotation, the sequence should be ABC. That's the only thing you have to memorize. And location of W, X, Y, Z, you don't have to care because it's a binary search tree. Where A can go, only place A can go, B can go. This is less than A. That's the only spot, right? How about value of W? So W should be between A and B. In the restructured tree, the range of A and B number should go as a left child of B. X, the value should be B and C. The only place it can go is left child of C. And anything greater than C should be stay with C in the right subtree. So if you only remember this, ABC, CBA should go ABC. And if you only remember that fact, you will be able to do this jig-jig rotation, right? Does that make sense for everybody? This is the part you have to memorize. The common error students try to do CBA, make it ACB. No, that's not right. It should be always ABC. After jig-jig rotation, the rotation tree should be straight. All 3 nodes should be placed in the straight way, and order should be ABC. And this is jig-jag rotation. Obviously, there is a symmetry case. Also, there is a symmetry case like this. So if you wanna, it's this tree after jag rotation, you have this tree, CBA, right? A, B, C after, when you make a C as a root of the tree, this is the resulting tree after that. So there are 2 symmetry cases, jig-jig rotation and jag-jag rotation coming from here to here. And there is a jig-jag rotation. For a jig-jag rotation, it's nothing but double rotation in an A-well tree. So you already have this idea, right? Grandchild will replace the root of the subtree, and B should be smaller than A, so B should be left child, C should be right child of A, right? And then we locate the subtree based on their value. That's A-well tree double rotation. A-well double rotation is identical to the jig-jag notation and jag-jig notation. So this is identical to LR rotation, right? In an A-well tree. So you don't really need to memorize it. You already have went through a number of examples, right? And there are 2 remaining rotation algorithms, and these are nothing but single rotation in an A-well tree, because if you are distance 1 away from the root of the tree, so now B is the root of the tree, I want to make A as a root of the tree. There's no way I can jump 2 level up. Then I push up left child. So we do LL rotation in an A-well tree. So make A pushed up, make a B as a child of A, Y become left child of B, right? So after LL rotation, so you will have this tree structure. The LL rotation is a part of splay tree notation when node is distance 1 away from the root. Obviously, there is a R rotation too, right? So if you want to make a B should be the root of the tree distance 1. So you can apply push of B, make A child of B, and Y become child of A, right? So you have a symmetry case for this. So we discussed 3 set of rotation. First, jig-jig rotation and jack-jack rotation in the reverse way. And then jig-jag rotation. This is nothing but Abel tree double rotation. And the last set of rotations are nothing but Abel tree single rotation. So the only new rotation is this. If you understand this rotation, you'll be able to do all splaying operation. So note that one of key difference between Abel tree and splay tree is splay tree does not maintain any height information. So splay tree, we try to minimize the overhead because the AVL tree has lots of overhead internally. It's a log n complexity, but we have to check the height again. Every node should maintain the height, and after insert, we have to check the left right of tree height and then do the rotation. So instead of doing that, let's have a simplified version of greedy algorithm. We try to improve the height of the tree after bad operation using those 6 rotations. That's a splaying tree notation. The splaying tree doesn't have any kind of height maintenance. And there is no guarantee that splaying actually improves the structure of the tree. It can maybe even worse than before splaying. But there is a tendency it will improve the height of the tree. And for example, in the left side of the slide, you will see a linear binary search tree. 7 is the largest element. Every element will be less than 7, so it will be in the keep adding, like adding 7, adding 6, adding 5, 4, 3, 2, 1. If you add in that order, this is the binary search tree you eventually have. And this one will go after splaying. Okay, let me use my DocCam for this discussion. So let me switch it to a DocCam. So first example of the splaying operation. So we have 7, 6, 5, 4, 3, 2, and 1, right? And then first operation was find 1, for example. So we found 1, then we have to do splay 1. So the discussion in the textbook, after every operation, we have to do splay. So that is the way the textbook discussed. So this is a jig-jig rotation. So our goal is make 1 as a root of the tree. The first step is a jig-jig rotation. So there's no change in the proportion of the tree. 7, 6, 5, 4. And order was A, B, C. After rotation, order should be C, B, A, right? So we know after rotation, it should be 1, 2, 3, not 1, 3, 2, right? So it was A, B, C, and after rotation, C, B, A. That's what you need to memorize. Okay, we have to still do the jig-jig rotation again, because we want to make 1 as a root of the tree, and no change for the root of the tree. 7 and 6 will be the root of the tree, and 1, 4, 5, the order should be 1, 4, 5, right? You just to build the structure of the tree, and the only thing we didn't add into the tree is the subtree. Where 2 should go? If you search it, this is the only place. So without memorizing algorithm, you will be able to draw the tree structure. The next operation is another jig-jig rotation. And when we do jig-jig rotation, 1 should be the root of the tree, and the right child of 1 should be not 7, because CBA should be ABC. So 1, 6, 7 should be the order, and this subtree becomes child of 6. Right? So that is the resulting splaying tree. Original tree has a height 1, 2, 3, 4, 5, 6, height 3. And this one has height 1, 2, 3, 4, height 4. There is an improvement on the structure of the tree, right? Is that 0, 1, 2, 3, 4, 5, 6? Yeah, 6 is correct. Yeah. Okay. So this is our first example of the splaying operation. So let me go back to my slide. Okay. I'm gonna ask you to try this exercise. Insert 5. And after inserting 5, you have to do splay. So this is a case you need to do zigzag rotation, a sequence of 1 jig rotation and zigzag rotation. So let me give you 2 minutes for this exercise. It's an easy exercise. So insert 5 and splay 5. So insert 5 and then splay. Okay, let's work together. So the first rotation is jig rotation. So this is nothing but a double rotation. So no change on the root of the tree. 3, 1, and 2. And then 5 will push up, and then parents become right child and grandparents become left child. And 8 should be still right child of 7. And next rotation is zigzag rotation. So after that rotation, 5 should be the root of the tree, and 3 should be left child, and 7 should be right child, right? That's how we did in the Abel tree rotation. Parents or grandparents will become left child or right child based on their value. And 8 bit stay with 7, and 3 will stay with 1 and 2, and 4 left child, only place it can go is right child of 3, and 6 become left child of 7. So that is the tree after displaying 5. And let's do one more exercise. This is the display tree with 5. I'm asking you to do add 0 for the last exercise before we take the break. Give 2 minutes and then we'll discuss solution and have a break. Okay. 0 should be left child of 1 because display tree is a binary search tree. This is the only place 0 can go. And then we have to do a jig notation. So this case, tree structure will be even worse than before displaying because that's the way textbook discussed. So when we do jig rotation, the 5 should be still root of the tree, and then 5 should have a 1 as a child, 0 as a child, sorry, and 1 become right child of 0, and 3 become the right child of 1. And 2 should be entered. So if it's not clear where 2 should go from algorithm, you can just enter 2 into the tree. This is the only place this one can go. If you check this one with algorithm, you'll find that, okay, this is a correct way to implement it. And 7, 6, 8. The last one is nothing but a single rotation in an Abel tree. So 0 become the root of the tree, and 5 become a right child. And since 0 doesn't have any left subtree, so it's empty left subtree, and 5 stay with 7, 6, 8 as is, and this the entire subtree become child of 5. So it'll be 1. Oops, I'm running out of space. 1 and 3, 2 and 4. Okay, so that is the resulting tree after adding 0 into the display tree given here. Any question up to this point? Okay, so we will take a 5-minute break. I will be back to the Zoom room by 6:06. Okay, see you soon. Hello. Let's talk about the delete operation. We didn't discuss find operation, find the maximum, find the minimum operation. Can we adapt the code from binary search tree to the display tree? Yes, right? Because display tree is nothing but a binary search tree with a special rotation. So find the operation, find the minimum, find the maximum. The code given in the binary search tree should work in a display tree also. So we'll not discuss those operations. We will discuss delete operation, the only operation we need to talk about. And as I mentioned earlier, the delete operation is the most complicated operation, and that's also true in the display tree. So sometimes maybe we can implement a lazy deletion like we did in the ABL tree. But lazy deletion is not very popular way to do it. The reason we discussed lazy deletion for ABL tree was we want to focus on the insert operation and the rotation, because if you can do the rotation and restructuring of the tree, delete operation is just the extension of that. So that's why we omit the discussion of delete and focus on the insert operation. Here, we do slightly different approach here. We will do actually delete operation on display. It's a little bit different. Um, if you want to delete the X, here is the sequence. First, we have to display X, and then display the largest node in the ref subtree. How to find the largest node in the ref subtree? We can use a find maximum code for the binary search tree. And then make the largest node in the ref subtree become the root of the ref subtree. Once you have that, we'll bypass X by making this is the largest node in the ref subtree. Largest node in the ref subtree is right child become deleting node's right child. Because of that, we can bypass X. As an example, here for delete 4 operation, we'll make 4 as the root of the tree. If you have the 4 as the root of the tree, and then we found the largest element in the ref subtree, that's number 3, and display tree. Display tree is within the subtree. Display tree make 3 as a root of the tree and 2 and 1 as a child of 2, right? That's the resulting tree after displaying 3. And after displaying 3, we'll bypass number 4, making ref child right subtree as my current right subtree, right? Make a 6 as a child of 3. Then, when you remove 4 from the tree, that's the resulting tree after delete 4. So delete operation in a displaying tree has 2 displaying operation involved. So here, maybe I can, as an exercise, maybe we can do, there's a one step not shown here why this tree become like that. There is a one more step not shown. So maybe I can show that for exercise 2.1. I'm writing down the tree on the handout. So let me switch to DocCam. Okay, here what we want to do is play 4. For play 4, first one is a zigzag notation. So 7 should be still root of the tree. 6, 5, not 5. That should be replaced by 4. And 2 should be left child. Stay with the left subtree. And 5 should be right child. And 3 become the right child of 2, right? So that is the first rotation result. And then next notation is the jig-jig rotation. For the jig-jig rotation, the order should be A, B, C, should be C, B, A, 4. B is 6. A is 7. And then we will just enter the subtree into the original tree. So 5 should go as a left child of 6, and 2 should go as a left child of 4. So then you will have this tree that's identical to the example given in the slide. Okay, right? So that's identical. So that's how I got this, and then explain the largest one, and then bypassing. So let's do. I want to have one more exercise for delete operation, but let me come up with an example. Switch to backend. So I did not prepare an example related to this exercise. I will just draw something. So let's do, let me add one more thing. Okay, let's say this is the tree, and let's do delete 5. So let me give you 3 minutes of your time for this exercise. For this type of question, you have to show at least 2 trees after displaying 5. Because if you make a mistake later, and if this portion of tree is correct, I will give you partial point. So so that I encourage you to give you some intermediate state resulting tree, then you will get some partial point. But if your answer is not correct, but I don't know how you got that answer, then it's very difficult for me to give you a partial point. Same thing happened for the midterm exam too. Some students missed all the inversions, and then minor mistake, I deduct small portion of the point. However, just a number like 15, what I can do? I don't know whether you just random guess or whether you counted it. But there's no way I can find it. So draw a tree after displaying 5, and then draw a tree after deleting 5. Okay. Draw 2 trees for this example. Actually, this example was not really well planned, so it's a very easy exercise. I think you probably, after playing 5, the largest node in the rep subtree already the root of the rep subtree. So you don't really need to do another play like this. Let me check if I am correct. Okay. The first rotation is logic rotation. So after rotation, 7 still be the and 3, 1, 2, and 5, 4, and 6, and still have 10, 8, 12. Okay. So we have to do zigzag rotation. So after zigzag rotation, 5, 3, 4 is not the root. Okay, yeah. Anyway, so it's very easy to play for next step. 7, 10, 8, 12 will stay with the 7, and 5 will send 6 to the left child of 7, and 4 to the right child of 3. 3 will stay with 1 and 2. So that's the tree after playing 5. And then deleting the first step, we found the largest element in the left subtree. That's 4. So play 4 within the tree. By the way, this is the answer for this part, right? When we do after playing 4, so 4 pushed up, 3, 1, 2 become a left child of 4, and 7 will bypass 5. So 7 entire right subtree of 5 become the right subtree of 4. So that's the resulting tree after deleting 5. Okay, any question for playing tree delete operation? Do you feel comfortable doing splaying and delete operation? Okay, that's, go ahead.
So when we delete the 5, we move the largest of the left up to the root.
Uh-huh.
Okay. All right.
Yeah, that's the algorithm. If you do delete splaying the smallest from the right, I will not say that's a incorrect answer because that's an implementation issue. But if you want to simplify my grading, please take the largest one from the left subtree and splaying. Then I have only one solution to grade. Otherwise, I have to come up with multiple solutions and consider all cases. Okay. And go ahead.
Even if that applies then, even if you're deleting in the right subtree, you still take the minimum or the largest in the left. Like say you wanted to delete 12, you would still take 4 as the new root of the subtree.
Deleting 12 from this resulting tree?
Yeah.
It'll be different. Maybe I don't think 4 will be.
But I mean, but you said we would. What I'm asking is would we take the largest of the left subtree? Like, is it from the root or is it from somewhere else?
So there's a 2 possible way displaying the largest from the rep subtree, right? That's what we did here, right? Displaying the largest element in the left subtree and bypass it. As an alternative option, you can display the smallest element in the right subtree and make 6 as a root of the tree. That's also a valid displaying operation, but not the algorithm given in the textbook. That was my comment.
Right. So what I'm asking is even if we were deleting 12, we would still end up with 4 as the new root after we.
Oh, if
did it.
there's a null tree, then what do I have to do?
No, if we're deleting from the right subtree, it doesn't, like, we still take the maximum from the left, though, is what it comes down to. Like, if we were deleting from the right subtree, like number 12, we would still take the maximum from the left subtree for our new root, is all I'm asking.
Yeah. So that's the algorithm in the textbook. Yes.
Okay.
For the last splitting step, the zigzag, we move the phi to the loop to the node, and then the node follow the right subtree is from phi it follow to A, right? Following the node phi. There will be.
I don't understand.
Yeah, just to pointing this tree.
This one? Okay.
Yeah, after the phi, and then there will be A or B10. You write is A, right?
5, 7, 6, 10, 8, 12.
Oh, after phi is 7.
Yeah, it's 7. Sorry. Yeah.
Oh.
This one is. Yeah, I'm sorry. Yeah.
Okay.
Because 7 is grandchild, so grandparent, so become the right child according to the algorithm. Yeah.
Thank you.
Sorry for my handwriting.
No problem.
Okay, so you prefer us to take the largest of the left subtree and not like the smallest from the right subtree?
Right. I want you to explain the largest one from the left subtree.
Okay.
Because that was the algorithm given in the textbook.
So if the left subtree is empty, do we take the smallest from the right subtree?
If left subtree is empty, then you just need to remove the root of the tree. You don't have to split if that's the case. Like if, for example, 5 doesn't have any left subtree, then after deleting 5, just 7. And 7, 6, 10, 8, 12. Right? Because there's nothing left here. So make a null and left subtree, we can ignore null. So right subtree becomes the root of the tree.
Okay, that makes sense.
Okay, so we schedule quiz tomorrow, and the scope of the quiz will be AVL tree and spline tree. So we'll discuss B tree, but we will not be within the scope of the quiz. And during the break time, I read through the message and comment from the Zoom room, and so one question was whether the final exam will be comprehensive or starting from chapter 4. The final exam will be comprehensive, but I will put more weight on the latter part of the chapter. So chapter 4, 5, 6 will be make it 75%, maybe 80% of question will coming from there. But chapter 7 and chapter 2, chapter 3, I don't think there is such important thing. But at least the chapter 2 question, chapter 7 question will be included in the exam. Okay, hope I want to clarify because you have only less than 2 weeks for the final exam, so give you enough time for preparation. Okay.
Could you just place this paper well so I can take a picture right now?
Okay. Yeah. Sure. Is that good enough?
You
want a deserting tree too.
You might go down a little bit. Go to the last solution. Okay. The last solution for the after deleting the file. Okay, I see.
Yeah,
right.
that's
Okay,
the bottom. That's the last one, the bottom part. Yeah.
Okay. Thank you.
Yeah, that's the solution. Yeah. Okay. Let me go back to my lecture slide then. So we are done for the display operation, and we need to talk about the execution time. Here we start use a slightly different execution time measurement. here we talk up to this point. We talk about worst case and average case. But here we introduce something called amortized complexity. And amortized complexity is the average cost of operation in the worst sequence of operation. So you have m number of operation, and what will be the worst case complexity for m sequence of operation, for example. So that is instead of single operation, we'll just group number of operation, and that group operation can be bounded by some equation. That's amortized complexity. So I will not go through the proof of amortized complexity of splay tree. If you want to see that, in chapter 11, I guess, there is a proof for the amortized complexity for splay tree. So I will just start with the conclusion. So if you have m operation in a splay tree, starting from empty tree, then there is a bound for the worst case cost for m sequence of operation. It's bounded by m times log n. So m operation bounded by m times log n. So average complexity amortized cost per single operation is about log n. However, the worst case complexity is still big O n in the splay tree. So the idea for splay tree is cost for big O n is bad for single operation. However, if it happened maybe once or twice, it's acceptable. So we try to prevent a sequence of bad operation by restructuring the code. So it was the proof that when you have an m sequence of operation from the empty spline tree, the worst case complexity is m times log n. So average complexity for single operation is about approximately log n. So that is the idea for the spline tree. I will go back to tree traverser because this one was somewhat related to your program assignment. The program assignment, you have to do something called the level order traverser. So I will discuss a level order traverser, and I will also talk about 3 different traverser algorithms we already discussed. First, if you want to print every element in the sorted order in a binary search tree, what do you need? Can you write down a code? You can easily find a code to do that, right? So it's very similar to what we did in the exam. The only difference is we have to visit the left subtree first, and then the current node and the right subtree. So what you need to do, you have to use the in-order traverser, right? What if we have to compute height of a node? Do we need to use in-order, post-order, or pre-order? If you have to compute height of a node, which one do you have to use? No idea. Post-order? Yeah, you're right. Why do we need to use a post-order?
Because you kind of get from the top down, so that I'm not too sure.
Okay, yeah, you're right. Yeah, the height of post-order is correct. Let's think logically. Can we compute my height without aware of my subtree structure? Probably not, right? Because height is by definition, distance to the farthest leaf node in the tree, in the subtree. So when we know the height of my left child and right child, what will be my height? Maximum of left child and right child plus 1. Does that make sense? So if you know the height of left child and right child, and then take the maximum, and by adding 1, you will be able to find the height of the current node. So let me show that code can compute the height. Then hopefully it'll be clear. Here I'm gonna say this is the integer. Integer is the returning value, and it compute height of the tree and binary tree t. So if t is equal to null, what should be the returning value? It's a tricky question, but we know the definition of
-1.
Right, exactly. It should be -1, right? Because we define the height of the null tree as a -1, so it must return -1, not 0. So otherwise, what we need to do, we simply return 1 plus. Let me use max function. Java has max function. It's just to compute height of t dot left. I will compute height of my left subtree, and then I will also compute height of right subtree. Compute height of left subtree, compute height of right subtree, and take the maximum plus 1. That's my height information. So that's the code can compute the height information. Does that make sense? If you have a tree and it has a left subtree and right subtree, if you know the height of left subtree root and right subtree root, take the maximum of that plus 1 will be the height of the node here, right? So we just apply this idea, and that's a common implementation to compute the height of the tree. And how can we compute the depth information? Which traversal algorithm do we have to use, and why? By definition, the depth is the distance from root to the current node. If I know the parent depth of my parent, I'm gonna simply do plus 1, right? Because my parent at depth k, my distance to the root will be k plus 1. So we have to compute parent first, right? Then you can label the depth of the child. That's nothing but parent depth plus 1. So we have to use a preorder. If you just Google the labeling depth, you will be able to find the code. You will notice that that's for preorder traversal algorithm. Because parents should know the depth first, and then children will have parents' depth plus 1. And the key discussion is the level order traversal. This is a part of your programming assignment. And for level order traversal, we'll start from level 0 and level 1, level 2, level 3, and so on. So we'll start from the root level 10, 5, 20. It always in the same level will travel left to right. And level 2, 2, 9, 15, 25. The last level, bottom level 1, 3, 7, 23, 30. That's a level order traversal, but it looks like there is a typo. 5, 20, 2, 9, 15, 25, 1, 3, 7. This one should be 23, not 18. So there is a typo. Sorry for the typo. Okay, so how can we print node according to the level order? That's what we want to talk about, right? So that's the part of the program assignment. If you use a queue data structure, you can easily implement it. The idea is when you visit a new node, I'm gonna put my left child, right child into the queue. And then I print my number, and then I will just move to the next round. Next round, I'll take out the first one from the queue, and then add the left child and right child of it into the queue, and then print current node element. So it's given here. The example code is given here. So this is what you need to implement for the programming assignment, and you don't need to implement queue. So you can just use standard Java library queue data structure for the programming assignment. So you can just implement the Java implementation of standard queue structure. So let me assume I have a queue, and that's a new queue, and then I have a binary node n, that's a binary tree, start from the root. So initially I place the root of the tree. Let me slightly use a better annotation. Root is A, so I'm gonna put root into the empty queue. And that's the starting point. Initially I have a root, and then I will take out the root and print root, and then put left subtree and right subtree B and C into the queue. And then I will take out something and print it, put left and right subtree into the queue repeatedly as long as the queue is not empty, right? That's the algorithm. Start from the root of the tree. So A should be inside the queue at the beginning. And I will repeat this code given here until queue is not empty. Sorry for the C++ code given here. It's the cout is like a system out print function. So here I will repeat that until queue is not empty, and then new node will be dq. So that will be the one we need to print. I'm gonna print element the standard output, and then include t left into the queue. T right is not null. I put that into the queue. For example, here after taking out A, the left subtree root B and right child C will be entered into the queue, and I'm done for A. I'm gonna returning back to the while loop, and queue is not empty because B and C is there. So take out B from the queue, and then add left child of B and right child of B, D and E into the queue and print out B. So that happened in the second iteration, and queue is not empty. Another iteration, C is the top of the queue, so I'm gonna print out C, and then add a child of C, that's F and G. So current queue include D, E, F, G, and then when I take out the next one, that's D, print out D, then D doesn't have any child, so nothing to add, so finish, and then going back to the while, and then next one is E, print E, nothing to add, move on, and then if you repeat that process, you can print everything in the level order. The pseudocode is given here, what you need to do for program assignment, just implementing this pseudocode for the one of the future function of your algorithm programming assignment.
I have a quick question.
Sure.
Is the pointer in C++ is the arrow? Can we use the dot operator?
Right. Right.
Okay.
So if I have to switch this to Java code, I should change this the dot notation, n dot element, n dot left, things like that, and no pointer here.
Okay,
yeah.
Thank you.
Okay. So I hope, Ennis, do you have an idea for the level order traversal? So if I use it, I cannot move to next slide. Happen again. So stop sharing, and then I will share my slide again. Okay, so we will do a B-tree discussion. And B-tree is a slightly different model. B-tree here, we try to minimize number of disk I/O operation. Up to this point, we assume every primitive operation takes the same amount of execution time. So we don't put any weight on some specific operation. However, here we try to add more complexity in the code to minimize number of disk I/O operation, because disk I/O operation is extremely expensive compared to the CPU execution time. So we are willing to add 1,000, maybe million of CPU operation to save several disk I/O operation, because disk I/O operation is the dominant execution time. So our BigO model does not strictly hold in this stage. So we assume entire data structure can be stored in the main memory, but that's not real world implementation of B-tree. B-tree was very popular in 1970s, 1980s, and B-tree was not popular after that because memory was cheap. So supercomputer, workstation, they got large memory, so most of data structure can be stored in the main memory at the same time. However, the importance of B-tree getting increasing because of the volume of the data, big data analysis, contention distribution network. The volume of data is terabyte or much bigger than terabyte range. So petabyte or something, so that it's not possible to store everything into main memory. So we have to store them into secondary data storage, such hard disk drive, the most popular one in current computing environment. So then we need to minimize disk I/O operation, because one disk I/O operation may be equivalent to two, maybe 1 million of CPU operation. It's extremely expensive. So we try to add more complexity in the implementation, and we try to minimize disk I/O. That's the goal. So this is the physical disk structure. If you have a chance to demolish hard disk drive, and you might find something similar, but it's just a theoretical picture and might be slightly different from actual hard disk drive implementation. But typically, hard disk drive has a multiple layer of disk. This is the area we store some information, and they are rotating. They are rotating in the very fast speed, and then so this disk will be divided into small sectors. The sector is a one I/O operation unit. So this sector should rotate, and going down below the head, at that point you can read the data. So if you just miss the sector, you have to wait the entire revolution of the disk, so that it may wait a longer time. But spinning speed will be much faster than the actual speed of arm moving back and forth. So there are multiple tracks in the hard disk, and track will be divided into small pieces of the sector. And the size of the sector is typically 4096 bytes. That's a typical implementation of hard disk drive. So if you want to write 1 byte of data into hard disk drive, you have to write 4096 bytes. You overwrite, same thing with the change of the 1 byte. If you need to read only 1 byte of data, you have to read 4096 bytes, because that's the I/O unit in the hard disk drive. So the rotation takes a very long time, and also delivering 4,000 bytes over the bus or some communication channel also important. And more importantly, the moving back and forth disk arm is extremely expensive operation. So we ignore that part. So that really device dependent. So we'll focus on the rotation time for this discussion. So anyway, there are multiple layers of hard disk, and they are spinning like more than tens of thousands times per second. So that's how they move, rotate. Then when this sector is under here of the reader, will be able to read the device, read the data from the hard disk drive. So this is a physical rotation. It's a very expensive operation. So this is a comparison between disk I/O versus CPU instruction, and we will consider 20 MIPS machine. The MIPS is a very old way to use and measure the computer execution time, CPU execution time. It's a million instruction per second. The 20 MIPS machine is like the machine in 1960s. So now we do not use a MIPS as a unit for comparing CPU anymore. So it's a very old machine. What I want to impose, want to explain here, it's a very old model in terms of machine, but hard disk, it's not, there's not huge gap. The MIPS machine is a very old machine. Now computer may be 100,000 times faster than this. So only 20 MIPS machine is like probably IPC XT, maybe 20 MIPS machine. It was introduced in maybe 1989, 88. So it's more than 30 years old machine. So it executes 20 million instructions per second. So it can perform 20 CPU operation in 1 second. But disk operation, so our assumption here, we assume disk can spin 3,600 rotations per minute. In the last slide, I thought I used the second as a unit, but it's a minute. So 3,600 rotation per minute. It's actual physical rotation. Even you use the fastest motor in the world, it really can really fast enough. So only 600 rotation per minute is the model given in the textbook. The real world hard disk drive, if you purchase low-end hard disk drive, it may be 7,200 rotation per minute. If you purchase high-end hard disk drive, it might be 14,440 rotation per minute, around that number. So there is not very huge, but a few times faster than this number, maybe 4 times faster than this rotation. And this is per minute. So it takes 3,600 rotation for every rotation. So single rotation will take 1/60 seconds. So from this discussion, we can do only 60 rotation in 1 second, right? So that we can read only 60 from the disk in single second if stored in the different sector. So on average, the half ton, right? So we can have 120 disk I/O per second. So here, 120 disk I/O operation is equivalent to 20 million instructions. So disk I/Os are extremely expensive compared to the CPU operation. So we try to minimize disk I/O operation by adding more complexity in the algorithm or in the code. So that's what we try to do. So dominant running time is up to the disk I/O operation, not the CPU computation. So we are willing to do lots of extra computation to save just a single disk I/O operation. So that's our goal. So suppose we are developing the system for the state of Florida, and we need to develop system that maintain driving record information for the entire citizen of the state of Florida. And we assume we have about 10 million items because many people has even not resident who are not citizen, they can have driver license. So we assume altogether 10 million items should be maintained, and each item has a 32 byte. In driving record system, the name is typically the key. So 32 byte will represent the name. Sometimes we will not be able to include the entire first name and last name, but it's a typical implementation, maybe a little bit old implementation. 32 byte reserved for the key to save the name, and then driver license record include height information, weight information, eye color, hair color, and some restriction and address information. It may have up to 256 bytes of information per single person. And we assume this is the shared system, so we can have up to 20 users on average at the same time. So you cannot use the entire system. You can have only 1/20th of the system resources. So based on that assumption, in 1 second, we can execute 1 million instruction because 20 million instruction is the instruction we can have every second. It's a shared system, 1/20 of that 1 million instruction. And how many disk I/O operation can you have? 120 divided by 20, only 6 disk I/O operation. So 6 disk I/O operation take 1 second of execution time. So let's say we try to implement that using binary search tree. In the worst case, we assume every record stored in the different disk location. So if you use a binary search tree, it may require 10 billion disk I operation because we're going down. It's a linear tree. We'll go down from the top of the tree. In worst case, it's a linear tree going down to the last one that require 100 million disk operation. It will take a very huge amount of time. But let's consider average case. When we use a typical binary search tree, the typical binary tree randomly constructed around 100 disk I operation because the height of the tree is about 100. And 100 disk I operation requires 16 seconds. 16 seconds is not really acceptable because users do not want to wait 60 seconds after submission of the query. So we need to find a better way. Okay, let's talk about the AVL tree based solution. When we use the AVL tree solution, okay, the worst case will be bounded by 1.44 times log n, so that it requires about 35 disk I/O operation. So it will take less than 6 seconds. But 6 seconds may be acceptable in the worst case, but we hope to be better. So typical case, how about the average case for AVL tree? It's about log n. So 24 disk I/O operation required. So we still need a 4 seconds of lagging time and delay. So our goal is, can we make 1 second of waiting time until from the submission of the query to the receiving of the query? How can you make a 1 second? The only way we can do is to reduce the disk I/O operation. So we want to make disk access to 3 to 4. So we are willing to add more complexity in the code, but problem is we cannot go better than log n complexity. So how can we do better? The idea is increasing the branch factor. So if you use a binary search tree, 1 disk operation, 2, 3, 4, 5. After 5th operation, we will be able to get the data and will be able to use the data in the binary search tree. However, if you increase the number of maximum children from 2 to 5, 1, 2, 3, after 3 disk I/O operation, we will be able to access every data, right? So that is the way we try to minimize the disk I/O. So the tree data structure we are talking about in this class, in this chapter, is like, oh, I can have 300 children, I can have 200 children, things like that. Instead of 2, we are talking about 300, 400. Obviously, the code for traversal algorithm, find the minimum, find the maximum, everything will be more complicated. However, that's okay because it can minimize the number of disk I/O operations. So the next class we'll talk about something called M-ORI branch vector. So M is the parameter. So that's the maximum number of children you can have. So in that case, we can significantly reduce the height of the tree. So it will significantly reduce the number of disk I/O operations. So that's for today's lecture. The couple problem will be up to the splay tree. The B tree discussion will not be within the scope. Any question up to this point? Okay? You enjoy the rest of the evening, and I will see you tomorrow. Okay? Thank you.
Thank
See
you.
you.
Thank you.
Thank you.